Sometimes, elephants are found trapped in pits. If I see this, I will find others to help with the elephants. But they are just too heavy to be pulled out of a pit barely with ropes. So, we should make use of some mechanical aids, such as pulleys. The way to apply them is pretty tricky. For example, these two pulley arrangements are basically the same, both cannot reduce the required effort to lift the elephant. But I have come up with a very efficient way. Believe me, even a 3.5 kilogram baby can lift an elephant with proper pulleys arrangement. Really? Really? 5-ton elephant can be lifted by a baby with the aid of pulleys. Do you remember this? Last time, we have introduced this arrangement of pulleys, and it works theoretically. But we further improve efficiency by adopting another pulleys arrangement. This time let's try another pulley arrangement like this. Trust me, we don't need several hundreds of pulleys this time. We just need 12, neglecting frictions in the pulleys and the weights of the pulleys. Now, you may pause the video and try to work on this yourself. Give you some hints, the minimum number of pulleys is 2. And there are 3 in this figure. There are 4 here. You may observe whether there are some common patterns in these cases. Okay? So, when you have finished, just resume the video to check your answer. Good luck. I believe some of you may find it difficult. I do agree that this question is not very easy. Let me explain to you step by step. Let's consider the first case, where there are only 2 pulleys. We are going to write some equations based on the conditions for equilibrium. Now, look at the elephant. There are 3 forces acting on this part of the system. 2 of them are the tension and the rope, and the remaining one is the weight of the elephant. So, the weight of the elephant is balanced by the forces of tension. And we find that T equals 25,000 newtons. Easy, right? Let's copy the result to here. Next, look at the baby. The weight of the baby should be balanced by the tension. But now we find that the force applied equals 25,000 newtons. This is much greater than the weight of the baby. Obviously, we need more pulleys. So, let's consider the second case. Analysis of this case is very important for us to find the final answer. So, pay attention. In this case, 1 pulley is added. Notice that there are 2 ropes here, not just 1. So, be aware that the forces of tension in the 2 ropes may not be the same. Now, let's consider several parts of the system. The elephant, the middle pulley, and the baby. Firstly, the elephant. The weight of the elephant should be balanced by the forces of tension in rope 1. So, we find T1 equals 25,000 newtons. Second, the middle pulley. Note that the tension in the rope below is T1, that is 25,000 newtons. Let the tension in the second rope be T2. The upward T2 forces should be balanced by the downward T1 force. Therefore, T2 equals half of T1. Finally, look at the baby. Obviously, the required applied force F equals to T2, which is 12,500 newtons. Still, F is greater than the weight of the baby. Before discussing the third case, let's see if there is anything special here. Have you discovered that, except for the part with the baby, the upward force of tension in the rope above the pulley is always half of the downward force on the pulley? Imagine if we add 1 more pulley to the current setting. Like this. The highlighted pulley is the newly added one. The arrangement of other things remains the same. So now, these 2 steps for the previous case are just the same for this case. Tension T1 is still half of the weight of the elephant. Tension T2 is still half of T1. The only change is the required force F, because the rope connected to the baby has changed to a new one. So, let's copy the results for T1 and T2, and consider only the highlighted pulley and the baby part. First, the pulley. Similar to the previous case, the upward force of tension T3 equals half of the downwards force of tension T2. Finally, we know that the applied force equals to T3, that means 6,250 newtons. After finishing 3 cases, can you see some patterns now? I believe you can realize that F is always equal to the tensions in the rope connected to the baby. That means, when there are n plus 1 pulleys, F equals Tn. You can check it with the previous cases if you doubt that. But what is Tn? Let's observe the pattern in case 3. Let's start from T1. T1 equals half of the weight of the elephant. T2 is half of T1. And T3 is half of T2. Now, can you see something special with the exponent of 0.5? Can you guess what Tn is? I believe most of you should have got the answer. Now, we can express F in terms of N. Also, we know that F is actually the weight of the baby, which is 35 newtons. As N is an exponent, logarithm should be used. Finally, we find that N should be around 10.5. Note that we need N plus 1 pulleys. So, we need at least 10.5 plus 1 pulleys, that is 11.5. No, we don't have half of a pulley. At least 12 pulleys are needed. But, remember, in reality, we should need more than 12. Why? Because we have neglected any frictions and weights of the pulleys for simplicity. So, what if the weight of pulleys are also considered? Hey, take it easy. We will discuss it in the next video. Before the end of this video, let's go back to basics. Do you remember these figures? At the beginning of the video, I commented these two pulley arrangements are basically the same, none of them helps. Do you know why? Let's look at the left one first. The weight of the elephant is balanced by the tension in the rope, and the man is pulling the same rope. So, the man has applied a force of magnitude equal to that of the weight of the heavy elephant. How about another pulley arrangement? Intuitively, more pulleys should help. But the truth is that improper pulleys arrangement helps nothing. This case is just similar to the previous case. The weight of the elephant is balanced by only the tension in the rope. At the same time, the man is pulling the same rope. At least, the force exerted by the man has to be the same as the weight of the elephant, not to mention frictions and pulleys. Now, can you see any similarities and differences between them? Try to compare with one another. It can help consolidate your concepts. Then, you will be confident enough to consider also the weight of pulleys in your calculations. Think twice before you like and subscribe.